In section 2.3, we're going to talk about how to write and interpret the symbols that depict the atomic number, mass number, and charge of an atom. These are used to describe the atomic structure of the atom. We're going to define the atomic mass unit and the average atomic mass, and then we're going to do some calculations. So, as we've seen, the nucleus contains the majority of the atom's mass. Protons and neutrons are much heavier than electrons. Electrons occupy most of the atom's volume. They're actually pretty far away on the scale of this from the center of that nucleus. If the diameter of an atom is approximately 10 to the negative 10 meters, the diameter of a nucleus is only 10 to the negative 15 meters. To put that in perspective, if an electron is flowing around a baseball stadium, the nucleus would only be the size of a blueberry at the very center. And everything in between those is going to be empty space. So atoms and subatomic particles are really small. They have really small values. To make this convenient to write, we're going to define some small units that mean that we don't have to express everything with these really large negative exponents. So we start off with the atomic mass unit, AMU. 1 AMU is 1.6605 times 10 to the negative 24 grams. And this is pretty convenient. So like now the mass of carbon 12, for instance, can be described as just 12 AMUs. And then we have our fundamental unit of charge, which is just the electron. And the electron is going to be equal to the charge of an electron in coulombs. This number that Mulliken came up with, 1.602 times 10 to the negative 19 coulombs. So, to give you some perspective here, one proton is roughly 1 AMU, 1.0073 AMU. It has a charge of +1. A neutron is slightly heavier at 1.0087 AMU. It has no charge on it. And an electron is much, much smaller at 0.00055 AMU, -1 charge. Atomic number. So the atomic number is the number of protons in the nucleus of an atom. This is the defining trait of an element, okay? All elements that have an atomic number that have 6 protons are always going to be carbon. All elements that have, say, 8 protons with an atomic number of 8, those are all going to be oxygen. So neutral atoms. In order for the atom to be neutral, we need the same number of positive and negative charges. Okay? So that means that if you are dealing with a neutral atom, you only have to talk about the number of protons, and then we can assume that there is an equal number of electrons to counterbalance that. Mass number. The total number of protons and neutrons in the atom is called its mass number. So we saw that protons and neutrons have the majority of the mass. When you add them together, really the mass of the electron is negligible. So we'll define their mass number as just the number of protons and neutrons. Also, because they are all roughly 1 AMU, the mass number is going to be really close to the actual atomic mass. So, in order to get the number of neutrons, what we need to do is subtract the mass number, or subtract the atomic number from the mass number. So our atomic number is the number of protons, our mass number is the number of protons and the number of neutrons. Subtracting them gives us the number of neutrons. So when the protons and electrons are not equal, the atom is electrically charged, and we call this an ion. We can figure out what the charge of that atom is by taking the number of protons minus the number of electrons. You can see that if there's more electrons, we're going to get a negative charge. If there's more protons, we're going to have a positive charge. And it's important to realize that atoms are only going to acquire this charge by losing or gaining electrons. They're never going to lose or gain protons in this process, because if they did, then they would be turning into other elements, and that would actually be like nuclear fission, or which we're not really going to get into here. So when the atom gains electrons, okay, it's going to get a negative charge, and we call that an anion, okay? When an atom loses one or more electrons, it's going to get a positive charge, okay, and we call that a cation. To remember which is which here, I've always kind of thought, well, cats are positive, so cations must be the positive one, and anions are the other ones, so they're negative. So chemical symbols. Chemical symbols, you've probably seen these before. They're the symbols that you see on the periodic table. They're used to abbreviate elements. Mercury, for instance, has a chemical symbol of Hg. A lot of them were derived from like really old names that they had for the elements and stuff. Some of them are other languages and stuff, so they don't always make a lot of sense to a native English speaker. But you just kind of remember them. Most of them have either one or two letters, but as they've been adding more and more elements, few of the newer ones down at the bottom actually have three letters. It's important to note that only the first letter of the chemical symbol is capitalized. That's going to be important later when we have to write out various different formulas and stuff. Here is an example that's mercury in a jar with its little symbol, Hg, on it. Here is a list of some of the more common elements and their symbols. So, aluminum, we have Al, bromine, we have Br. Those ones all make pretty good sense, but every once in a while you get something like gold is going to be Au. This is from an ancient Latin word, aurum. Iron is going to be from ferrum, one of the old words for it. And lead, we have Pb from plumbum, which I really like that word. So the symbol for a specific isotope of an element is written by placing the mass number as the superscript to the left of the elemental symbol. And I'm going to show you some examples of that. Down here we have magnesium. We have magnesium 24. Magnesium 25, that's going to have one more neutron than magnesium 24. Magnesium 26, it's going to have two more neutrons than magnesium 24 and one more neutron than magnesium 25. But all of these are all going to have the same 12 protons. Here is a little breakdown of how we're going to write all of the things that we've talked about so far. You put the atomic number in the bottom left here. You're going to put the mass number in the top left here. And you're going to have the charge up here in the top right. And in this book, they typically write it as a number followed by a charge. That's how I'm going to want you guys to do it in the homeworks and stuff when I ask for this. Some other texts, they'll actually write plus and then 2 after that. But this is the way that we're going to do it. So here's an example of isotopic abundance. So we have hydrogen. And hydrogen has three different forms. You can have protium with 1 neutron, you can have deuterium with 2 neutrons, or you can have tritium with 3 neutrons. And you can see that they only differ in the number of neutrons that they have, and each one is therefore going to have a different mass. And they also have a different natural abundance. So 99.989% of the hydrogen you come across is going to be protium. Only 0.0115% is going to be deuterium. And tritium is so rare that it's difficult to say even how much there is. We barely ever see any tritium. So we saw that we got to talk now about atomic mass. We saw that each proton and each neutron has a mass of approximately 1 AMU. Each electron weighs far less. Therefore, the atomic mass of a single atom in AMU is approximately equal to its mass number, but not quite. But because most elements exist naturally as a mixture of 2 or more isotopes, the periodic table actually lists a weighted average of all of the isotopes present naturally occurring. That's where these longish mass values that you're going to see on the periodic table come from. So let's see an example of that. In order to do a weighted average, you're going to take the abundance of one of the isotopes and you're going to multiply it by its mass. Then you're going to add that to the abundance of the second one, multiply it by its mass, add that, on and on until you've done all of the different isotopes that element has. We have an example of this in our homework with a video that I did explaining this in a little bit more detail. But let's look at our example here. If 19.9% of boron is boron 10, and it has a mass of 10.0129 AMU, and 80.1% is boron 11 with a mass of 11.0093 AMU, then its average mass is going to be this value here as a decimal times its mass there plus this value as a decimal here times its mass, and that's going to give us an average mass of 10.81 AMU. Little sanity check, we can see that that's between these two values, and it's closer to the one that is more abundant. The occurrence and natural abundances of isotopes can be experimentally determined using an instrument called a mass spectrometer. Basically, the samples are vaporized and then they are exposed to high energy electron beams, and it kind of removes electrons from the sample, making them charged, and then it's focused through onto a detector using magnets. So here's an example here. We start off with our sample and we heat it, and then we hit it with this electron beam and we get it all good and ionized, and then we have these electrodes here that are going to accelerate it out as a coherent particle beam, and then we deflect it with the magnets, and then it hits the detector, and depending on where it hits on this detector we can tell what the mass is here. So if this has a pretty high mass, then what it's going to do is it's not going to deflect very much and it's going to strike right around here. If it has a low mass, then it's going to be deflected quite a bit and it's going to strike more down here. And we can figure out the isotopic abundance if we put in a pure element in here. These are actually used to do all sorts of really great science. A lot of CSI work and stuff where they inject something in and it tells them everything about who the killer was and stuff. They're using an equipment a lot like this.